Hi guys, and welcome to the third teaching video in Physics 1.4, where we're going to talk about diffraction. So this video is going to talk about what diffraction is, how diffraction changes with different wavelengths, and a couple of practice questions on diffraction. So what is diffraction? Diffraction is the physics behind how you can get cell signal when there's a hill between you and the cell tower. So it's essentially the bending of a wave when part of it is stopped by a barrier. So in diffraction, if part of a wave is stopped by a barrier, the wave can bend around and continue at the edge of the barrier. So in this case, part of the microwaves from the cell tower are stopped by the hill, but they can diffract around the hill and reach the ground on the other side. Waves that have longer wavelengths bend more around a barrier. So in this case, this wave has a smaller wavelength, so the degree of diffraction is less. So if this was a hill and you were standing where the arrow is, you wouldn't actually be able to get cell signal. This example has a bigger wavelength, and the degree of diffraction is more. So if you were standing in that same spot, you would actually be able to get cell signal, because it can bend more around the barrier. If diffraction happened to every single wave, we would be able to hear someone around the corner and see them as well. But we can't see people around corners without mirrors, but we can hear them. Sound has a relatively big wavelength, so when it undergoes diffraction, it bends quite far around a barrier. This is why we can hear someone from around the corner. Light, however, has a very short wavelength, and if you remember from before, waves with smaller wavelengths bend less around a barrier. And since light has a very short wavelength, it hardly bends at all, and this is why we can't see someone from around the corner. Diffraction is commonly seen in waves of water, with very big wavelengths. Cell signals, which are just microwaves, are harder to get around hills than radio waves, and this is because they have a smaller wavelength and diffract less than radio waves. So what effect does diffraction have on the wave itself? The person that you're hearing talking behind the corner doesn't sound any different. They don't sound suddenly very squeaky or very deep. This is because the frequency, speed, and wavelength of the wave do not change. It's very easy to remember. Diffraction doesn't have an effect on any of the wave's properties, just the movement of the wave. You can see that the wavelength before it hits the barrier is exactly the same as the wavelength after it hits the barrier. The frequency and speed and wavelength of the wave don't change. And the wave isn't entering a different medium either. It's not suddenly traveling from air to water. All it's doing is traveling through the same medium but hitting a barrier. And since the wave isn't entering a different medium, the velocity is going to be constant. The only thing that changes in diffraction is the direction of the wave. Here are some questions. Once you've read the question, think in your mind about how you'd explain it in an exam situation, then press play to reveal the answer. If you're walking along a cliff back from the edge, how can you hear the waves break but not see them? This is due to how sound and light diffract. Sound has a big wavelength, so when part of the sound wave is stopped by the barrier, the rest of it bends around the cliff and can reach your ears. And this is why you can hear the waves break. However, the light from the waves breaking is a very short wavelength, so when part of the light wave is stopped by the cliff, it doesn't bend very much at all, so your eyes can't pick it up. Why does there have to be more cell towers, which use low wavelength microwaves, than radio towers for accurate coverage around hills? This is what we talked about before, where the low wavelength microwaves diffract less around hills, so are harder to pick up by cell phones, than radio waves, which have a big wavelength and diffract more. When big ocean waves are diffracted by an island, what happens to their wavelength? What about their velocity? Diffraction doesn't change wavelength at all, so the big ocean waves, when they're diffracted by an island, have exactly the same wavelength as before. Because the waves are not suddenly changing between water to air, the speed of the wave in that medium is going to be constant, so the velocity is not going to change. So here's what you need to know from this video. We talked about what diffraction is, which is essentially just the bending of waves around a barrier. When part of a wave is stopped by a barrier, the rest of it can bend around. The direction of the wave can change, but everything else, so amplitude, wavelength, frequency, and velocity, is constant. Waves with a bigger wavelength, such as sound and water, diffract more and can bend more around a barrier. Waves with a smaller wavelength, such as microwaves and light, bend less around a barrier.